All right. We are at 7-2. And we're doing this chapter a little bit differently because, well, it was done differently based on what was available for students back in those days. So we're at page 249 or page 255, depending on which textbook you have. And 7-2 is rational and irrational roots. Now let me just start reading at the bottom of that page. You recall that a rational number is a real number, such as 3/4, 2 1/3, or -9, which can be expressed as a ratio of integers. So the question is, can you express numbers such as square root of 2, cube root of 5, and -4th root of 3 as ratios of integers? Do you see that another way to state this question is to ask whether the equations x squared equals 2, which is another way of stating the square root of 2, what number squared equals 2, y cubed equals 5, which is another way of stating the cube root of 5, and z to the 4th equals 3, which is another way of stating negative the 4th root of 3. Isn't that a typo there? I don't see where the negative is on the last one, but I'm going with what the text says. All right? Okay. Top of the next page, it says, to investigate the conditions a rational number must fulfill to be a root of a polynomial equation with integral coefficients. Okay, so don't get all caught up in the big words. Polynomial equation, right? That's just a many-termed equation, right? So it's a number of terms. Okay, usually 3, but it could be 4 terms, whatever. How do I know what the terms are? Well, generally speaking, plus or a minus sign separates the terms. It gets a little more complicated than that, but that's an easy way to think about it. With integral coefficients, well, that's just a fancy way of saying the numbers in front of the letters are integers. First, consider the particular equation 21x cubed minus 14x squared plus 30x minus 20 equals 0. All right, so let's think about that equation. Is it a polynomial equation? Yeah, it's many terms. 1, 2, 3, 4 terms. Okay. Does it have integral coefficients? Yeah, the number in front of each letter is an integer. Okay. Now, in the text, in fact, I'll just bring over my digital copy here. In the text, we can see that they give us they say that this polynomial equation with integral coefficients has the root 2/3 as shown by the substitution. And you can see the substitution for x with 2/3, and they work this equation, they simplify the equation, or the expression at least, and they get 0 equals 0, which makes it true. Okay, here's what they then say. Do you see that 2, the numerator of the root 2/3, is an integral factor of -20, the constant term of the equation? Okay, so is it an integer factor? Yeah, it is. You factor 20 and 2 times 10, right? Notice also that 3, the denominator of 2/3, is a factor of 21. Wait, what? 21? Well, that's the coefficient of the term of highest degree, the leading coefficient, right? So the 21 right here, 3 times 7 is 21. What we have observed leads to the following theorem about rational roots of a polynomial equation in simple form. That is, an equation having 0 as one member and a polynomial as in simple form as the other member. Okay, the members of the equations, the one member, the 0 on the right side, the polynomial in simple form on the left side. What's simple form? Well, simple form would be integer coefficients, and in descending order of degree. Okay? And so what is the theorem there in the middle of that page, 250 or 256? If P and Q denote integers, where Q does not equal 0, such that P over Q is in lowest terms and represents a rational root of a polynomial equation in simple form with integral coefficients, then P must be an integral factor of the constant term and Q an integral factor of the leading coefficient in the equation. Okay, so looking at the example then at the bottom of that page, they give us x squared equals 2, and we're supposed to find rational roots. Okay? Well, remember that our theorem, or our example, that led to our theorem is our polynomial equation is to be in simple form. And it's generally a good rule. Whenever you see something like this, although frankly, this is relatively easy to solve, but whenever you see something like this, set it equal to 0. Okay, so we can take this and we can say x squared minus 2 equals 0. All right, understand why that becomes minus 2. Hopefully you understand how that happens. All right, so here's simple form. What do we care about when we're trying to determine rational roots? Okay, well, we're trying to get the P over Q. The P, we care about what's there, the number in front of, or the number that is the leading coefficient, the coefficient on the term of highest degree. And the Q, we care about the constant term. Okay. Right, so in this case, for the P, wait, did I do those backwards? No. I did do those backwards, didn't I? Arg. Ignore what you just heard and let me fix it. Okay. The P, we care about the constant term, and the Q, we care about the leading coefficient. Okay. There. Now we have it correct. All right. So for the P then, we're interested in the factors of -2, right? So that could be -1 times 2. It could be 1 times -2, and I'm not aware of any other factors. So there's 4 factors to consider: -1, 1, 2, -2. All right. So for the Q, we're interested in the leading coefficient here is a 1. It's not a 0. It's a 1. When there's not a coefficient written, the coefficient is 1. And so what are the possibilities here? Well, I guess there's 1 times 1 and -1 times -1, right? I guess. So at the very bottom of that page, 250 or 256, the only rational numbers to test as roots are the 4 integers: 1, -1, 2, -2. Why? Well, the 1 is common to both, the -1 is common to both. So there's really just 4 different possibilities. And so on the next page, page 251 or 257, we run the test. Does 1 work? No. Does -1 work? No. Does 2 work? No. Does -2 work? No. So what does that tell us? That tells us that x squared equals 2 has no rational roots. Okay. Now let's take a look at what that looks like graphically. Okay, let's say that y equals x squared, right? And then let's say that y equals 2. Now you're going to notice when we say that it has no rational roots, it doesn't mean it doesn't have any solutions. Okay, so look at our graph here. Let's zoom in on it a little bit. Look at our graph here. There are solutions, and in fact you can see that it's 1.414, and that's probably truncated or chopped off, and negative 1.414, right? So there are solutions. Those decimal numbers are not rational numbers. What does that mean? They can't be written as a fraction with an integer as the numerator and the denominator, okay? So back to our textbook, page 251 or 257, whichever. From this example, it follows that square root 2 and negative square root 2, the roots of x squared equals 2, are not rational numbers. Now notice we could include the negative square root 2, because remember that's the book's notation to say the negative square root, right? All right. Real numbers which are not rational are called irrational numbers. They can't be written as a fraction of integers. By considering the equation x to the n equals b for any integer n exceeding 1 and any positive integer b, you can see that the nth root of b is an irrational number unless b is the nth power of an integer. Thus the cube root of 5, negative the fourth root of 3, and the seventh root of 64 are irrational numbers. Okay, I need to read that again. Considering the equation x to the n equals b for any integer n exceeding 1, so whenever n is greater than 1, and any positive integer b, you can see that the nth root of b is an irrational number unless b is the nth power of an integer. Okay, the nth power of an integer. So think about 2, right? Is there an integer that raised to whatever power equals 2? No. 1 squared is 1, 2 squared is 4, right? So that tells me irrational. Okay, so what I want to do for 7-2 is I want to direct your attention to problems 15 through 22, okay? And I want to show you how to solve these using our Desmos calculator. And I don't want you to think of this as cheating or anything that way. This is using the tools that are available to us. Okay, now, and you know, if you continue with your education and if you go beyond this algebra 2, if you start getting into calculus, having a graphing calculator in your advanced math is going to be important, and that's what this Desmos.com is. Okay, so I want to show you how you can use it to find the rational roots of the given equations, numbers 15 through 22. So I'm going to do a couple of those, and then the rest of them I'm going to have you do this way. All right, so again, we're using Desmos.com/calculator. Anyway, you want to be at their graphing calculator as you see it here. And let me get all of this in. Okay, so here's how we want to do this. Okay, looking at number 15. So what I want to do is, notice that number 15 is given to me as y cubed minus 2y squared plus 5y minus 4 equals 0. Okay, so what I want to do is set this up. Since they used y, I want to set this up as saying that x equals this equation, right? So we'll do y, and to do the cubed, I'm going to do this a to the b, and whoops, let me back that up. I wanted to do all my keystrokes on the screen here. X equals y cubed, and then I'm going to arrow over. Notice how my cursor changed. So I'm not, if I left my cursor up there, the next thing I entered would be up there. Okay, and I don't want that. So I right arrow, so I get a tall cursor, and then I can do the minus key, 2y squared, then plus the 5y, plus 5y minus 4. Okay, so now I have this graph. I can zoom in and out and see this graph. Okay, now this next step, I'm going to show you this next step to show you something else. You won't necessarily have to do this to find your solution, but let me just show you, right? So this equation right here, I've got to set equal to x. Now what we're interested in is the solution when x equals 0, okay? Well, when x equals 0, that's just the y axis, right? That's where x equals 0. And so we're interested in this point of intersection, and notice that when x equals 0, y equals 1. So 1 is a rational root to the given equation. Okay? 1 is a rational root to the given equation. Right? And that's the only rational root when x equals 0, because it's the only point of intersection. Okay? So again, how did I do this? I set the given equation equal to x, and that graphed the equation here for me. And then I set x equal to, in this case, 0. Okay, and in fact, that's the way you would always want to do these. But frankly, you can just know it's the y-intercept. Okay, that's your solution. Now, what's kind of cool here is that I can use this slider, right? And I could let x be whatever I want. If I set this equation equal to 1, then the solution is right there, and y is 1.233. Okay. But again, we're interested in it where x equals 0. Okay. So when you look at numbers 15 through 22, rearrange numbers 17 and 18 so that they're in that simple form. Descending degree and set equal to 0. See, now once I've got this set this way, I can just manipulate this first equation. But the fact of the matter is, since I'm interested in the y value where x equals 0, okay, I don't even really need that second, right? Because it's, in fact, it always, whenever you do this equation right here, enter this equation here, it always marks the intercepts for you, okay? And we're interested in this one. Why? Because that's where x equals 0, and the equation is set to 0, right? I don't think it allows us to do 0 equal, yeah, see, it goes crazy. Well, actually, it doesn't go crazy. It actually shows me what the solution is, 1. That's interesting. All right. So let's do this. Let's look at number 16. I'm going to enter it exactly as it's shown in the text. And let's see if this works, because this one actually has multiple roots. We'll see what happens here. So y, a to the b, I'll put a 3 there, and then I'll do that right arrow, so I'm ready to do the next. Minus 6y squared plus 11y, see, I'm not sure this one's going to work, minus 6 equals 0. Hey, it did work. All right, so I entered it exactly as given in the text, and what it's showing me is that solutions are 1, 2, and 3. Let's see if that's correct. 1, 2, and 3, that's correct. Yep. How do I know it's showing? That's the lines that it's given here, right? It's 1 on the y-axis, 2 on the y-axis, and 3 on the y-axis, right? So that's pretty interesting. That was number 16, right? I can just enter it and I can get the solution, right? Now, again, I don't want you to think that, oh, well, this is cheating, we're not doing it right. No, this is making use of a graphing calculator, which is a tool that is available to us, and we should use, okay? Or we can use to our benefit. So let me try number 17. And for number 17, I'm going to enter it just like it's shown in the book. We'll see what happens here for our solution. If this pulls this off, then this Desmos calculator is pretty cool, right? So number 17, I'm going to enter it just the way it is. Now, I don't have the letter Z, so I'm just going to, instead of putting Z in, I'm going to put X. Well, no, I'm going to, yeah, I'll just put X and we'll see what happens here. So X cubed minus X squared equals 14X minus 24. Okay, that's pretty impressive, right? Look at where it intersects the x-axis. Because I used x, now we're interested where it intersects the x-axis. It intersects at +2, +3, and -4. And there's my rational roots to this equation. 2, 3, and -4. Okay? Is that pretty cool? I hope you think so. All right. So I want you to do numbers 15 through 22, and I've shown you how to do a couple of these. You've got your keyboard here, right here, to enter things. Now, if you need to enter a fraction, right? So if I wanted to do a plus and a fraction here, if I just treat that fraction as a division, for example, 2/5, if I do 2 divided by 5, okay, now I get my fraction, right? So you just treat, like on number 19, that 3/2, just treat it like a division. Just do 3 divided by 2, and it'll set up as a fraction for you in the equation, okay? So, and you're going to need to use either X or Y in your equations here. So instead of using their letters like their T, use an X or a Y. And if you use an X, then what you're interested in is where these lines intersect the X-axis. If you use a Y, you're interested where they intersect the Y-axis. Okay? And you can find the rational roots of these using your Desmos.com calculator. Okay? Desmos.com/calculator. And this is nothing you have to sign up for. You'll notice that I'm not logged in. I mean, you can sign up and you have ability to save things and such. It gives you a few more functions, but for everything we'll need to do, you can just go there and use it, and it will work for you. Okay? So numbers 15 through 22, let me write this down. You're going to use Desmos.com/calculator. And for 7-2 written exercises, numbers 15 through 22. All right? Get comfortable using that calculator and finding your rational roots. Okay? And I want you to pay attention to the number of rational roots that you get and compare that to the equation, okay? Right? So in other words, this last one we did, looking at the equation, why is it interesting that we got 3 rational roots? Okay. Yeah, maybe that's not as interesting as I thought. Yeah, never mind about that. Don't worry about that. I was thinking of something else.